everyone, myself Dr. Ashok Babu. So in this video, I am going to discuss about the stub matching of a transmission lines. First of all, transmission line can be used as a matching section by inserting between a load and a source. So I repeat once again, transmission line can be used as a matching device. Matching device means it is used to match the input and outputs. Matching device, matching section by inserting between load and source. So here it is possible to connect the sections of open or short circuited line called stub in shunt with a main line at some points or point to effect impedance matching. This is known as a stub matching. So I repeat once again, stub. What is a stub? So here the stub may be a open circuited line, or it may be a short circuited one, or it is connected, a open or short circuited line, it is connected to the main line of a transmission line to affect the to adjust the impedance or to affect the impedance matching. So this is known as a stub matching. To adjust the impedance, we need to add some open or short circuited line to a main transmission line. So due to the addition of open or short circuited line to a main transmission line, the impedance may decrease or the impedance may increase. Or to balance the impedance, we will use the open or short circuited line. So this is nothing but a stub. So here we have some advantages of a stub. A stub matching can be used for length and characteristic impedance of the line. So that is remain unaltered. So for that purpose, we can use the stub matching. So it can be adjustable. It can be used to adjustable susceptance are added in shunt with the line. So due to the stub matching, the susceptances are added in shunt with the line. So here these are the two advantages of a stub matching. This is the first one, stub matching. Second one, advantage of a stub matching. So here we have mainly two types of stub matching: single stub matching, double stub matching. So we will discuss one by one briefly. First one, single stub matching. So here let us assume a transmission line. It is a transmission line. So a load is connected at the output of a transmission line. So here we will connect the source at the input side. Okay. So here a stub is connected in between the source and load to adjust the impedance of a transmission line. This is known as a stub. So here we will connected a single stub. So here we connected a short circuited stub. So here we may connect the open circuited line also. So let us assume it is a short circuited stub. So which is having the length LT, length of the stub is LT, and which is placed at a distance of LS from the load. So let us assume a transmission line. A short circuited stub is connected to a main transmission line. The length of the transmission stub is connected to a main transmission line is LT, and which is placed at a distance of LS from the load. So like that you assume a stub matching. So let us consider a transmission line having a characteristic impedance, a characteristic admittance. So here we can use the impedance Z0 and we can use the admittance Y0. So here let us consider a transmission line having a characteristic admittance Y0 terminated in a pure conductance YR. So let us assume it is a YR. It is the receiving. It is at the receiving end, and which is having a characteristic impedance Y0. Since the stub is parallel with the main line, so here since the stub is parallel with the main line, the admittance can be added. If it is impedance, then we can find out the impedance by using some mathematical method. Because here it is we are finding the admittance. So these two are parallel to each other. So the total admittance is equal to the addition of two admittances. So when YR is different from Y0, the standing waves are set up in a transmission line. So when these two are equal, so when Y0 equal to YR, then a matching may occur. So due to the matching, we cannot have the standing waves in a transmission line. So if Y0 equal to YR, then we have standing waves, in a transmission line. Next, when the line is traversed from the point of maximum conductance to that of a minimum conductance, obviously, so there will be a point at which the real part of the impedance is equal to its characteristic impedance. When it is moving towards the transmission line at some point, so there will be a point at which the real part of the impedance is equal to its characteristic impedance, its characteristic impedance. So here we are assuming if a suitable susceptance obtained by using an appropriate length of short circuited or open circuited line. Here we may use the short circuited line or we may use the open circuited line to adjust the susceptance or to adjust the impedance of a transmission line. So let us assume for that, let us assume we know that the impedance of a transmission line. So here we know the impedance of a transmission line is Zn. Zn is equal to, it is Z0 into Zr plus Z0 tan HPL by Z0 plus Zr tan HPL, where P is nothing but the propagation constant. So here we can have P is equal to alpha plus J beta, where alpha is attenuation constant, beta is a phase constant. So in place of P, where P is a propagation constant, here we can write the alpha plus J beta. If alpha equal to 0, then we can write P is equal to J beta. P equal to J beta. So like that, we can have we know the already impedance of a transmission line. From impedance, we can find the admittance of a transmission line, because it is easy to calculate the all admittance of a transmission line when we add a stub. So let us assume in place of impedance, assume admittance of a transmission line. So here the admittance Yin is equal to, it is Y0 into YR plus Y0 tan HPL by Y0 plus YR tan HPL. So from this we can find out the normalized impedance value, admittance value. So here for high frequency line, we can assume P, we can have the P is equal to alpha plus J beta, alpha plus J beta. Therefore, for high frequency line, we can substitute alpha equal to 0. Therefore, P equal to, we can have J beta. P equal to, we can have J beta. Therefore, and change the admittance into normalized admittance. If we change the admittance into normalized admittance, then we can have the equation. So here the normalized admittance means it is Y in by Y0. Y in by Y0 becomes a Y small in. Here Y in is the normalized admittance value. So here already we have in equation we have in previous equation we have Y capital N is equal to, it is Y0 into, so here we have YR plus Y0, YR plus Y0 tan HPL by, so here we have Y0 plus YR into tan HPL. So this is the actual equation. So here if you find the normalized equation, it is Y in by Y0 is equal to, so here we can take a common of Y0 in both numerator and denominator, then it becomes YR by Y0 plus tan HPL by, so here also if we take Y0 as a common, we have 1 plus YR by Y0 into tan HPL. So here in place of Y in by Y0, we can write the normalized admittance value. It is Y small in. Y small in is the normalized admittance value. Therefore, Y in small in is equal to, here also we have Y in. YR by Y0 is the YR by Y0. We can assume it as Y small r. Y small r is the normalized admittance value. YR plus. So here in place of P, here I am substituting J beta. Therefore, it is becomes tan H J beta L by, so here we have 1 plus Y small r into tan H J beta L. So here tan H J beta L is nothing but the, so tan J theta, it is just like tan H J theta, tan H J theta equal to J tan theta, tan H J theta equal to J tan theta. Therefore the equation becomes, so Y in is equal to YR plus in place of tan HJ theta. So here directly I am writing J tan BL by 1 plus J into YR into tan beta L. So here if you rationalize the equation, then, so here to rationalize the equation, we need to multiply and divide the equation with 1 minus J YR tan beta L by 1 minus J YR tan beta L. Therefore the equation becomes Y in is equal to, so here if you multiply the two equations, it is just like 1 plus A plus B into A minus B. Therefore A square plus B square. So A square minus B square, A square minus B square is, here we have J square is there. Therefore 1 square plus YR square tan square beta L. So in numerator, if you multiply the numerator, Then we have yr into, if you multiply and separate the terms, then we have yr into 1 plus tan square beta L plus j into 1 minus yr square into tan beta L. So here we can separate the real and imaginary parts. So here if you separate the real and imaginary parts, then we can have here the real part is equal to, so first part is yr into 1 plus tan square beta L by 1 plus yr square tan square beta L, and the imaginary part is 1 minus yr square into tan beta L by 1 plus yr square tan beta L. So it is both imaginary and real parts. So for no reflection, we can have yin is equal to y naught. For no reflection, yin is equal to y naught. If yin is equal to y naught, or we can write yin by y naught equal to y1 1, or y small n is equal to 1. We can write y small n equal to 1. So where y small n is the normalized admittance value. So thus the stub has to be located at a point where the real part of normalized admittance is equal to unity. Where the real part of the normalized admittance is equal to unity. Therefore, the real part of the normalized admittance is here yr into 1 plus tan square beta ls by 1 plus yr square tan square beta ls, which is equal to 1. So here we can cross multiply the equation, and if readjust the equations, so here it is, we have yr into 1 plus tan square beta ls is equal to, we have 1 plus yr square tan square beta L, yr square tan square beta ls. So here if we readjust the equations on both sides, and here we have yr plus yr tan square beta ls is equal to 1 plus yr square tan square beta ls. So here if you take tan square beta ls common on both sides, so it is tan square beta ls into yr square minus yr is equal to yr minus 1. So here in these two, we can take a common of yr common. Therefore, yr into it is tan square beta ls into, so here if we take a common of yr minus 1 is equal to yr minus 1 on both sides. So here we can cancel the yr minus 1 on both sides. Then we have tan square beta ls is equal to 1 by yr. But yr is nothing but, already we know that yr is equal to yr by y capital R is equal to y small r equal to, it is capital R by y capital R by y naught. Y capital R by y naught. Therefore, 1 by root yr means root of y naught by yr. This equation becomes tan beta L is equal to root of y naught by yr. Root of y naught by yr. So here it is capital again. So this equation gives the location of the stub ls, where ls is the distance between the stub and output. The distance between the stub and output, and can further be simplified as, so here we know that tan beta L is equal to root of y naught by yr. Therefore, beta L is equal to tan inverse of root of y naught by yr. So here we know that beta is equal to 2 pi by lambda. Therefore, 2 pi by lambda into ls, which is equal to tan inverse root of zr by z naught. So here in place of admittance, here we are using the impedance. Therefore, ls is equal to lambda by 2 pi into tan inverse root of zr by z naught. So where ls is it is a location of a stub, or it is a distance from the output to the stub. So ls is equal to, so from figure we can observe that. So if you go back to the figure, so it is a ls. So ls is it is a distance between the stub and output. So it is a minimum distance required to place the stub. So now the susceptance at the location of the stub will be. So here we can calculate the susceptance, where bs is nothing but the susceptance. Therefore, bs by y naught gives the susceptance of a stub. So bs by y naught is equal to real imaginary part of the admittance. So here the imaginary part of the admittance is, it is 1 minus yr square into tan beta ls by 1 plus yr square into tan beta ls. So here substitute the values of tan beta ls in the equation. Already we know that tan beta ls equal to root of y naught by yr. Tan beta ls equal to root of y naught by yr. So here if you substitute the tan beta ls in the equation, so here 1 minus y square into tan beta ls into, so tan beta ls means it is root of y naught by yr here, it is root of y naught by yr here, by 1 plus yr square into, so in place of tan square beta l, in place of tan square beta l, so you can write y naught by yr, y naught by yr. Therefore here yr means nothing but, again yr is nothing but the y capital R by y naught. So here I am replacing the normalized to actual admittance value. Therefore it is 1 minus yr square by y naught square into root of y naught by yr, root of y naught by yr, by 1 plus yr square by y naught into y naught by yr. So here if you simplify the expression, we can simplify the expression. So here yr cancel each other. Therefore we have y naught cancel each other. Therefore we have 1 plus yr. We can have the only 1 plus yr in the denominator part. 1 plus yr by y naught in the denominator part. In numerator we have again 1 minus yr square by y naught square into root of y naught by yr here. Therefore here we can write the expression as 1 minus yr by y naught into, it is 1 minus 1 plus yr by y naught into root y naught by yr, by we have 1 plus y naught by yr is there. So here we can cancel these two. Therefore we can have the bs by y naught is equal to 1 minus bs by y naught equal to, we have 1 minus yr by y naught into root y naught by yr, root y naught by yr. Therefore here again if you simplify the expression, here take LCM. If you take LCM, it is y naught minus yr by y naught. Therefore we can simplify the expression. It is just I am writing here bs by y naught is there, bs by y naught into, so here if you take LCM here, it is y naught minus yr by y naught into root of y naught by yr. So here you can cancel y naught on both sides. Therefore the equation becomes bs is equal to, it is y naught minus yr into root of y naught by yr, root of y naught by yr. So it is a susceptance value that is connected to a main transmission line to adjust the impedance matching, or to adjust the impedance, or for impedance matching. So here the susceptance that should be added at this point by the stub BS, so which can be obtained either by open circuited or it can be obtained by using the short circuited stub. So here the short circuited stub is invariably used because in all practical applications you can use a short circuit. So it is because, so it radiates less power than the open circuited one, or its effective length may be varied by means of a sharding, bar, which normally takes the shapes of sharding plugs. So because of these two advantages, for all practical applications we will use the short circuit stub only. So here the susceptance of lossless short circuited stub is, it is a y naught cot beta LT. So it is a standard value. The susceptance of a short circuited stub is, y naught into cot beta L. Therefore where LT is the length of the short circuited stub. So therefore if we equate the susceptance, in place of susceptance, if we write the admittance value y naught cot beta LT, we can find out the LT value. Therefore, so from the equation cot beta LT is equal to, so it is y naught minus yr by root y naught into, so just I am readjusting the equation. So after readjust the equation, here we have, so cot beta LT equal to y naught minus yr by y naught into root of y naught by yr. So which is equal to, so here we can readjust the equation as, so it is y naught minus yr by, it is root of y naught into yr. If you cancel the y naught, in numerator and denominator, we have y naught minus yr by root y naught into yr. So here it is a cot beta LD. So if you write the tan beta LD equal to, so it becomes an impedance opposite value impedance. It is root z naught zr by z naught minus zr. So here from this we can find out the beta LD. So it is beta LD is equal to, you can write the tan inverse root z naught into zr by z naught minus zr. Or LT is equal to, we can write 1 by beta into, it is tan inverse root z naught into zr by z naught minus zr. Or beta is equal to, we know that lambda 2 pi by lambda, we know that beta is equal to 2 pi by lambda. Therefore, the length of the stub which is used for balancing of a transmission line is, it is LT is equal to lambda by 2 pi into, it is tan inverse root of z naught into zr by z naught minus zr. So this is the length of the stub that is used for the stub matching. So it is about the single stub matching. So here we have some disadvantages of a single stub matching. So it is useful for fixed frequency only. It is useful for the fixed frequency only because, so as the frequency changes, the location of the stub will have to be changed. So it is one of the disadvantage of a single stub matching. So for final adjustment, the stub has to be moved along the line slightly. So we can move the slide towards the left hand side, or we can move the line towards the right hand side. So here this is possible only in open wire lines, and because here we are using, for all practical applications, we are using the for utilization of less power, we are using the short circuit line. So it is one of the disadvantages of a single stub matching, and therefore we are using the open wire lines, and therefore on coaxial lines a single stub matching may become inaccurate in practice. So because of this two reasons, we cannot use the single stub matching for all practical applications. So to avoid the advantage of a single stub matching, we can use the double stub matching. So it is the double stub matching. So here to overcome the two disadvantages of a single stub matching, so here the two short circuited stubs. So here we are using the two short circuited stubs. It is the first stub. It is the second stub. We are using the two stub matchings whose lengths are adjustable independently, but whose positions are fixed, maybe used as shown in figure. So here in previous one, we can adjust the stub, we can move the stub towards the left hand side, we can move the stub towards the right hand side. So whereas in double stub matching, we are fixing the two stubs at a particular point. So we are fixing the two stubs at a particular points, and we can use the stubs at a different frequencies. In previous one, we have a disadvantage that we can use the stub at a fixed frequency only. Whereas in double stub matching, we can use the stubs at different frequencies. So it is one of the advantages of a double stub matching. So here, if you observe the figure, so here we have two short circuited stubs. So first one is having the length LT1, second one is having the length LT2, and these two are placed at the distances of LS1 from the load and LS2 from the, and here from first stub, it is a distance of LS2 to the second stub. LS2 is the distance of the stub from first stub. LS1 is the distance between the output and single stub, first stub. So this is about the some brief introduction about the double stub matching. So here we will have some small derivation for the stub matching. So let the first stub whose length is LT1 be located at a point A at a distance of LS1 from the load end. Then the normalized input admittance at that point is, the normalized admittance value is, so here let us assume YA. Therefore the normalized admittance YA is equal to Y capital A by Y naught, which is equal to, we have already equation with known equation, YR plus J tan beta LS1 by 1 plus J YR tan beta LS1. So where YR can be assumed as a pure conductance, if you rationalize the equation, with 1 minus J YR tan beta LS1 by 1 minus J YR tan beta LS1, then the equation becomes like this. So here in your denominator we have again same as the previous one, 1 plus A plus B into A minus B, just A square minus B square, because we have J j into j minus j square minus 1 minus minus plus. Therefore, it becomes 1 plus yr square into tan square beta ls1. So here also we can separate the imaginary and real parts. So here the real part is yr secant square beta ls1 by 1 plus yr square tan square beta ls1 is a real part of the equation, and 1 minus yr square into tan beta ls1 by 1 plus yr square into tan square beta ls1 is the imaginary part. So here this is equal to, let us assume, imaginary part and real parts. Admittance is equal to real and imaginary parts. So where G is the conductance, B is the susceptance. G is nothing but the conductance. G is nothing but the conductance. B is nothing but the susceptance. So here the real part is equal to conductance, imaginary part equal to susceptance of a given stub matching. So here GA, imagine the real part is equal to GA is equal to, it is yr secant square beta ls1 by 1 plus yr square into tan square beta ls1, and the imaginary part becomes BA is equal to 1 minus yr square into tan beta ls1 1 plus yr square into tan square beta ls1. So when a stub having a susceptance B1, let us assume the stub is having a susceptance B1, so is added at this point, the new admittance value will becomes, so if you add the susceptance, then the new admittance becomes, let us assume the admittance is ya dash, so ya dash equal to GA plus GBA dash. So here if you observe this equation, adding of susceptance will increase the susceptance value only, but there is no change in the conductance value. But adding of susceptance will increase the susceptance value. Since only the susceptance value is altered by the addition of the stub, the conductance part remains unchanged. Therefore, unchanged, it should be of such a value, the admittance value YB equals 1 plus Z beta 2. So where 1 is the real part of the admittance or conductance of the conductance of the transmission line. So here the stub length at B is adjusted such that the new value is 1 to affect the matching. So here we need to adjust the stub matching. We need to adjust the second stub so that the conductance value of the stub is equal to 1. So like that we need to adjust the stub without affecting the frequencies or without affecting the other characteristics. So here if you adjust the transmission line stub like that, then we can have a effective matching. If conductance equal to 1, then we can have the effective matching in the transmission line. So here the distance ls1 can never before than or equal to lambda by 2. It means the length of the transmission line ls1 should be less than lambda by 2 only. For effective matching, the length of the stub should be less than lambda by 2. So in which case the input admittance looking towards the load repairs itself automatically. So this distance will always be less than lambda by 2. Therefore the general length of the stub can be chosen for all practical application it is from lambda by 4 to 3 lambda by 8. So it is the general length of the stub to for a better matching purpose. So the distance of ls1 is generally is of the order of 0.1 lambda to 0.15 lambda, so that we can have the effective matching than a single stub matching. So this is about the double stub matching, single stub matching and double stub matching. Mainly double stub matching will avoid the two disadvantages of a single stub matching. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.